Okay, so it's 3 p.m. I will start the class, and so what was I saying? Yeah, so quantum information theory. So there's a lot of things to explore there, but I guess most people are here already, so let me get started with today's class. Today we are starting a new chapter. So all these few chapters are quite short, so we finished the gravity chapter already, and today we will be talking about chapter 8. So chapter 8 is about oscillations. Okay, so I'll go to full screen. Okay, so so today we are talking about oscillations, and basically it is a type of motion that is repeating over and over again. So this chapter is a little bit abstract, and in case it gets abstract, like, we just remember when we talk about oscillation, we just imagine a spring, right? So if we imagine a spring sitting on a horizontal surface, right, and then if we pull and let go of the spring, it will go left and right, right? So it's like oscillation. The spring motion will oscillate, and today we are studying this type of motion for today, right? So that is about the oscillation. So to start with a new topic, usually we need to introduce a new concept, right? So I wanted to say oscillation is the most important types of motion. As you go higher and higher level, right, you realize that a lot of the advanced topic, most of the time the example is always simple harmonic oscillation. If you go to quantum mechanics next semester and next year, you will spend at least 2-3 weeks studying the quantum harmonic oscillator. So that is important thing, right? And if you learn the thermodynamic chapter, I don't know if it's being covered, to derive the formula for heat capacity, you actually assume that the particle is oscillating. Okay, anything wrong? Why cry? Yeah, because nothing, but for now it's not difficult yet, right? So everything is all come back to oscillation. Okay, so that's why it's very important. And like even the deeper levels of theoretical physics, quantum field theory. So quantum field theory is also, like, at the end of the day, right, you have a quantum field. You want to describe how the protons and particles interact with each other. When you quantize it, you're actually using the harmonic oscillator again, right? So everything depends on the harmonic oscillator. So that is the most basic type of motion in physics, actually, right? More basic, I would say, than the chapter 1 and chapter 2 kinematic equation, because a lot of things will undergo oscillations. Okay, so let us introduce some new terminology. We will talk about, firstly, period and frequency. We already been using those words before, but we have been using those words when we were discussing circular motion. And if it's a uniform circular motion, right, our period is the time taken to go one round, and then the speed, you can calculate the circumference divided by the period. This t is the period. It's the how long does it take to go one round, right? So this is a circular motion of an object. So that one we have seen this before already. So this is we have been using those words when we are talking about circular motion. Why? Circular motion is one example of a periodic motion. Okay, so I would emphasize we're talking about uniform circular motion. Okay, so uniform circular motion is an example of a repeating motion. Okay, so repeating motion is to make it more clear, right? It's something that repeat over and over again, but the more official terminology, so what we call it, is the periodic motion. So today we are studying periodic motion. Okay, so what is a periodic motion, right? So a periodic motion, I should define, right? So a periodic motion is a type of motion that repeats identically after a finite time, which is t, and this t is the period. Okay, so this t is the period. Okay, so that's why circular motion is a periodic motion, because after one period it will start a new circle again. It's another circle. After one period, another circle. So every time a new circle. So every time is one circle of motion. So that is the periodic motion. Okay, so yeah, so our Earth's rotation is a periodic motion, right? Our Earth rotate one round every 24 hours. That is a periodic motion. Our Earth's orbit around the sun is also periodic motion. Our Earth goes around the sun every year, 365 days. So every 365 days, repeat again. Okay, so the elliptical orbit, not just circular, right? Elliptical orbits that we have learned in the previous chapter, because after the ellipse, it will repeat over and over again. So that is another example of a periodic motion, and this is what we are be talking about today. Okay, so this is periodic motion. It's repeating after a finite time, right? Finite time, because if t is infinity, that means is something new until infinity. So that's not a periodic motion. Okay, more terminology. Sometimes, right, you see textbooks, they will say one period, they will use the word cycle. So one period is also called a cycle. Okay, so it's also called a cycle, right? And then of course, when it comes to period, right, a period is just a measure of time. So the SI unit is seconds. It's just time measurement. So that's why the SI unit for big T is seconds. But sometimes the question will give you in terms of hours or days or years, but you can always convert back to seconds. Okay, so that is the concept of the period we have learned before, so I'm just reminding you, right? So repeating. But there's something else that we've been using, but now we will focus more frequently, is the frequency. Okay, so frequency. Frequency is just 1 over period, so it's the inverse of period. So frequency, usually we call frequency f, but sometimes they call the Greek letter nu, but we seldom use this. It looks like v, but it's another letter. So to avoid confusion, we call this f, so it's 1 over t. And then therefore the unit for frequency is 1 over time. So it's t minus 1. So the SI unit for frequency is 1, well, we call it 1 hertz, and 1 hertz just means 1 per second. Okay, so it's inverse second, right? So this is hertz, and sometimes hertz for short we write just Hz. So 1 hertz is just 1 per second. Okay, so that is the SI units for frequency. Okay, so we have talked about period, we have talked about frequency, and then the different words for one period. So so other terms that you might also see in like most books or online or lecture notes is sometimes they give the unit of RPM. So RPM is just rounds per minute or revolutions per minute. Revolution is just one cycle, right? How many cycle you can go within 1 minute? So cycles per minute, right? So that is one way. Or sometimes they just give it as cycles per second. So when you see all these words, it just usually is easy to translate back to say what it means, how many rounds you can give per second. Okay, so that is the basic ideas of periodic motion. Okay, so the one place where you can see the unit of the unit things, right, is when you are driving a car, right? So if you are driving a car, on one side is how fast you are going, right? So the speed. Then the second meter they give you is called the tachometer. This one tell you how fast the engine is running, right? So I don't know if you recognize what this is, but usually, right, if you see the engine, the meter is the unit is 1000 RPM. So if you press your pedal, right, and then the engine runs until you hear the sound, and then it goes until 2 or 3, it just means 3000 rounds per minute, right? So let's say you drive a car, right? If you drive a car, right, and then you see the meter goes at 2, so it means it's 2000 RPM. So 2000 RPM is actually a quantity that you can measure in terms of frequency and convert it back to SI units. So 2000 RPM is 2000 rounds per minute, right? So it's 2000 per minute. So if you convert to per second, you times 1/60, right? So end up you have 33.3 cycles per second. You use it when you're learning driving. Why don't people put hertz there? Yeah, so it's like convention. Hertz. People do use hertz for radio, right? Your frequency, like your radio station, they give you the hertz, like 92.5 FM, like that number, and that is a hertz. It's also cycles per second. Okay, so yeah, maybe it's because it's designed by engineers, and for engineers it's more convenient. So you get 33.3 hertz. So that is megahertz. Yeah, so for radio station is for megahertz, right? Something like translational, no, it's like time. So you can say it's the translational in a time direction. So because hertz has related to time, the 1 over the period. So that's all, right? So that is for the yeah, you can see the numbers of rotation. Yeah, how many rounds it can go per second. So it's easier to imagine, I would assume. Right? So that is for frequency, right, in cycles per second. Another quantity that is more convenient if for physicists, right, not engineers, but for physicists, for us, if we are doing calculation, so mathematics as well. If you're doing calculation, then it's more convenient to use angular frequency. We have also used this quantity in circular motion a little bit, right? But now we use it more. So let us talk about angular frequency now. So angular frequency is just nothing but 2 pi times the frequency. Okay, so it's just 2 pi times frequency. Okay, so so the symbol that is being used is omega, right? It is similar to your angular velocity symbol, but right now it's for angular velocity, and it's equals to 2 pi f. Okay, so this is the angular frequency, and of course the SI unit is the reason why they use the similar symbol is because it's a similar dimension. It is radians per second. Okay, so because 2 pi, you times 2 pi, you are changing this into a unit of radians already. Okay, so in the tachometer example, right, for the driving car, right, so we have 2000 RPM. We have convert this to 33.33 hertz, and if you times 2 pi, so it becomes 209.4 radians per seconds. And usually we use radian more common, right? We seldom use degrees per second. Radians is a more natural measure of angle for most of this chapter. So these are the situations that we encounter quite often. Okay, so yeah, so let's start with an example. That's true. Electrical stuff normally is for hertz, like your power supply, right? The power supply for Malaysia is 50 hertz, that kind of thing. Right, your AC circuit vibrates, oscillates once every 50 seconds. Okay, so let's see how this works by working out example 8.1.1. Okay, just a simple thing. I have an ultrasonic transducer. What is this? I also don't know, right? But we don't care because we just want to do this. It's something to do with medical equipment, and the frequency is megahertz. So the frequency, let's write this down, 6.7 megahertz. So mega is 10 to the power 6, right? So it's 6.7 times 10 to the power 6 hertz. Okay, so the question is asking how long does each oscillation takes and what is the angular frequency. So very easy. each oscillation takes how long means it's asking for the period. So the period should be 1 over f. So it's 1 over 6.7 times 10 to the power 6. So if you get this, you get 1.5 times 10 to the negative 7 seconds. Because the frequency is very high, it takes a very short time to complete one cycle, right? Because the thing is going very fast. Okay? And then to get the angular frequency is very easy, just 2 pi f. Okay, so 2 pi times this, so you just 2 pi times 6.7 times 10 to the power 6. And then the answer is 4.2 times 10 to the power 7 radians per second. Okay, so we got this now, right? So that is pretty straightforward. Okay, so any questions so far? Let me check. Okay, so if there's no other question, then everything's still very easy, right? Just introducing some names and terminology. So if everyone already knows what is this, then we can go ahead to do the first oscillation motion that we will study in this course. It is the simple harmonic motion. Okay, so an example of a simple harmonic motion is the spring. By the way, right, I have an announcement. I forgot to tell you. Let me say it now before I forget, because I will definitely forget. Next Wednesday, so next Wednesday, right, we have to start our class at 4 p.m. because I got online meeting with main campus, and it will drag, and it will, so to be safe, I will start the meeting. I will start our lecture from 4 to 6. So I hope that is okay. I sent the announcement already. Okay, our normal lecture time is 3 to 5, right? So we have to do it on 4 to 6, but only for one day, only for next Wednesday. Is everyone okay with that, right? Just one day, just one day. Our quiz is next Wednesday. Yeah. Yeah, so our quiz is, we will standardize every time Wednesday, right? So our quiz is automatic, so you guys can do it by yourself. So it will start as normal. Then if you can't make it, then got video lah. So you can watch the video after that, right? It's only one day. It's only one day. After that, back to normal. Okay. Yeah. So that is the thing I want to make. And then also, yes, quiz Wednesday. Our chapter cover is 6 and 7. The rotation and the gravity, right? So that's the thing to think about for next week. Okay, so yeah, so I'm just saying it now before I forget. So now it's done, that we can now focus on simple harmonic motion. Okay, so what's a simple harmonic motion? Simple harmonic motion, I will call this SHM for short, because it's so long to write every time. Simple harmonic motion happens when the system is experiencing a linear restoring force. So I will explain what the words mean after I finish writing this sentence. Okay, so what is a linear restoring force, right? So we are talking about simple harmonic motion. It happens for linear restoring force. So linear restoring force, it just means that the force is equals to a negative constant, and then times a displacement. Okay, so as you can see, right, it is an example of a conservative force, because this force is position dependent only. Okay, and I need a negative constant also. And then why is it called a linear restoring force? The reason is because we are specifically wanting the case that the power of the displacement is 1. So linear is called linear because the power of displacement is 1. So if I have a displacement square over here, then it's no longer linear restoring force already, right? Or sine of displacement, or exponential of displacement, like no longer linear. So I want linear. Okay, so force is a vector. It has magnitude and direction. Magnitude is the magnitude, right? And then the direction is the negative so it's always negative to displacement. And as you can see, right, this is how we can get a harmonic motion, because linear restoring force, right, is like when the displacement is 0, I have no force. Then if I move somewhere, the force will push me back here, right? And then I move the other way, it's always opposite, right? And this is and because of this, right, so a spring is something like this. So if I have some, it will ends up to become a harmonic oscillation. Okay, so this is the system that we want to solve over here. And to be more concrete and easier to understand, we will solve a specific system, for example, the Hooke's law. Okay, so a Hooke's law is, we can imagine a box of mass m, right? So a box of mass m, and again we consider the center of mass only, right? And then let's say this is the equilibrium position. So equilibrium position is x equals to 0, and then I have a spring, right? So this is some position of x. Then what is the horizontal force acted by this object, right? So we can draw the free body diagram. Then we have the horizontal forces. But firstly, let's start with Newton's law, right? So Newton's law is in the horizontal component, F is equals to ma, of course. But by Hooke's law, the force is negative kx, right? So this is a linear restoring force, and then this is equals to m times a, right? Because if you draw the free body diagram, if I pull the string this way, the force is acting this way, right? So it's always trying to push you back towards the equilibrium. And then if I squeeze the box until here, then the force will try to push it back the other way. So it's always opposite to your displacement away from equilibrium. So this is the situation that we have here. Okay, so everyone should be able to follow this so far, right? We have learned this in chapter 2, nothing new, right? So nothing new, but the new thing comes here. Okay, so right now, right, I want to write the acceleration as, well, acceleration is the second derivative of position with respect to time. So what we have here is actually a differential equation. Okay, so this is negative k over m times x. Okay, so I got this equation now, right? So this is so this one is a second order ordinary differential equation. Okay, so the students from MAT, you guys are learning how to solve this already, right? And then but the MAT one, you have solved more different cases compared to this, but physics student, you will learn it in the next, you will take this course in the next semester. But for now, right, I'll just show you the solution for this simple case, right? So we only want to do this for this simple case, and a slightly more complicated case later. So we just want to study these two things for now, for our context, right? Separate from MAT. But sometimes some example of MAT may use this as well. Okay, so let's show you how to solve this. Okay, so yeah, so solving the ODE. So wait, by the way, before, is there any question? Yes, the stable equilibrium. Yeah, I didn't say that. Yeah, so the spring here is supposed to be the stable equilibrium. Yeah. By the way, right, because of the, as you can see, why the linear restoring force gets a simple harmonic motion, because, right, the force is always trying to make it such a way that it will oscillate. So if let's say if I pull the string, right, until this position, and then I start from rest. So if I let go from rest, what happened? The spring will pull it here. So it will increase in velocity, right? If I increase in velocity, it gains in kinetic energy. By the time it reaches 0, it has velocity, so it will overshoot, right? So it will overshoot and then come here. By the time it comes here, the spring will try to get the opposite direction already, so it will slow it down. It will slow down until here, and then 0 velocity. But 0 velocity, there's a net force, because the spring is being compressed. Then it will try to push it back, right? And then go to here. So it will keep on going like this, back and forth, back and forth, back and forth. Okay, So that is the simple harmonic motion that we have over here. Okay, so how do we solve the solution? So again, right, learning how to solve a second order is in your math course. Nothing to do with here. Here I will just tell you the solution. So the general solution is, I want to know what is the x, right? So differential equation, I have this equation. What is x? Okay, in particular, what is x as a function of t? Because I want to know the position at the object at different time, because at initial time is here, some later time is somewhere else, it keep on going back and forth. So I want to know x in terms of t. Okay, so the general solution is very simple. For our case, it's just a constant cosine omega t plus phi 0. So it's just a cosine function. Have you learned this before in your high school? Do we need to solve the equation during final exam? Yeah, no need to solve, because I'm already just telling you the solution like this. You may need to do it in your math course, because the math course is where you learn how to solve. Okay, but at least, right, to convince you, don't worry about exam, but at least to convince you what I'm telling you is true, right? I want to convince you that this is true. Let's check that this is a solution. Okay, so this, I will call this equation 1. So does this function satisfy equation 1? So check that solution satisfy equation 1. Okay, so to check, right, well, I need to know the second derivative, so I need to differentiate this 2 times. So if I differentiate this the first time, actually it gives me the velocity, right? But yeah, differentiate this the first time, what do I get? So on this side, differentiate, this is a constant. Okay, so the general solution is, the a is constant, these are some constants independent of time. So if I differentiate this, I only differentiate the t. So differentiate cosine gives me a negative omega, right? Okay, and then I differentiate again. So differentiate the second time. So that will give me my acceleration. But if I differentiate this the second time, the omega come out again. So omega square and then a, and then cos omega t plus phi 0. And then you see something familiar. This part is the same as the original thing that you started with. So this is just x again, right? So this is just x all over again. So what I have here is dx dt is negative omega square x, right? So this omega square, does this satisfy equation 1? Let's look at equation 1. Okay, so this will satisfy if this constant is equal to this constant, right? So it will satisfy if, well, from here we find that omega square is equal to k over m, or in other words, omega is the square root of k over m, right? So that means the solution that we should write is x of t is equal to a cosine this thing, right? So square root k over m t plus the constant. But usually it's very messy to write the whole thing, so we just keep it as omega, and we know omega means this. Okay, so this is the solution. Okay, so it's satisfied provided that this is the solution. So the general solution is x of t is equal to a cos omega t plus phi 0, and the omega is given to be k over m. Oh, don't cry, because we are not doing integral, right? We just, this is nothing, yeah, we only differentiate, no integral here. Yeah, so luckily for us, no need to do integral now. Okay. Now, so remember, right, just now what we are saying is that our omega, right, so omega, because omega is 2 pi f, so I got 2 pi f is equal to the square root of k over m, And then from here we can also get t, so 2 pi over t is equals to k over square root m, and we got the period of a spring harmonic motion. This is m over k, the square root. So this is the period of oscillation. Okay. So just to remind you, right? So because of all this relation, omega is what? Omega is 2 pi f, and therefore omega is 2 pi over t. So there's another way you can write this, is that my x of t is because of this is my omega, this is a cos, then I got 2 pi over the period t plus phi 0. So I'm just showing you various ways to write this function, but at the end of the day it's always this function over and over again. Okay. Also the derivatives are there, but derivatives should be much easier, right? Much easier than integrals. Okay. So yeah, but the more you do it, the more used to it. So the more you get used to it, then it will be good, right? So how does it look like? Well, it's a cosine function. So the solution is just a cosine function, right? So let's plot the cosine function. So in terms of t, right, the cosine depends on the period of oscillation. So if I draw, let's say I draw until here. So one period is like this. Then this is t half. Then this is t over 4. This is 3t over 4. What does my function looks like? This is the a. So the cosine should be from negative a to a, right? So from negative a to a, and then when t is equal to 0, it depends on the phi. So let's say, for example, I want to draw a simple case just to show you. If my phi 0 is 0, so if my starting point should be like this, right? Okay, so this is the graph of x is equals to a cos omega t, right? So this is the oscillation. So this is a periodic motion. So after t, it will repeat again, right? So every period of t, it will keep on repeating the same motion over and over again. That's why we call it a periodic motion. Okay, so now we also need to know this one. Also, you learn a lot in the calculus course also. What happens if the frequency is double? If the frequency is double, right, what's going to happen? It's going to become like this, right? Yeah, my drawing is ugly, but hopefully I get it right. Okay, so this is x is equals to a cos 2 omega t, right? So if this is some omega naught, right, then it's the double frequency. So 3 omega t is faster, and so on and so forth, right? So that's how you get the spring oscillations. Okay. Any other question? Okay, right, that's true, right? The more you practice, the better you get. So yeah, then in fact, I told you guys already, right? Physicists usually do math faster than mathematicians. I have seen this all the time. Like the differentiating a function, integrating a function, factorizing a function. Because math, at deeper level is like more abstract and more theoretical and more talking about theorems. But physicists always do that like forever, their whole life. So if they work together, right, usually they do it faster than physics one. The physicists will do it faster than mathematician. So one thing I want to talk about is this. So the period is given by this formula, and this is the formula that is usually taught in the high school. So the period depends on the if you remember, right, I forgot to define, but I'm assuming everyone knows. Over here, m is the mass of the object, mass of this thing, right? So this thing has mass object, and then this is the spring constant. Okay, so this is m and this is k. Then after we calculate, I found that my period is m over k square root times 2 pi. So from here we get some various situation. If m is large, then t is large, right? So if m is a higher number, then t becomes a higher number. So m is large, t is large. So if t is large, it means what? It takes a longer time to go one period. So it is a slow oscillation, right? And then what about if m is small, t is also small? Okay, so for a large m, t is large. So a heavy object, right, is because it's heavy, so it goes very slow, right? So it makes sense to what our imagination expects. Okay, if k is large, this is dividing by k. So if k is a large number, then square root 1 over k is a smaller number, so t becomes small. So small period means higher frequency. Higher frequency means faster oscillation, right? So what does it mean by large k? The k means the strength of your spring. So a larger k means the spring is very tight, right? It's a stronger spring. It's a stronger spring, so it will pull it back more faster and you make it oscillate faster. So that is that is what happens to the k. If k is small, it's a weaker spring, right? It's very loose. So it's very loose also, you get a slower oscillation. So it depends on the ratio m over k. Okay, so large k means stiff, right? So we call it a stiff spring. Stiff means very hard lah, right? So that is the nature of the k. Only trigonometric functions satisfy this property. You mean the harmonic oscillations, is it? No. Well, this is interesting because not just sine and cosine, but a sum of sine and cosine. So yeah, I think in the future you will learn about Fourier series. So in general, sums of trigonometric function, right? Most periodic function can be expressed as a sum of periodic function. Oh, he mentioned Schrodinger equation. Okay, that's interesting. Yeah, so Schrodinger equation is an equation for quantum mechanics, and a lot of the solutions are periodic solution as well. And yeah, and why he mentioned, I imagine Schrodinger equation is important because it is in linear algebra. When you solve a Schrodinger equation, you want to find the energy. The energy is the eigenvalue and things like that. By guessing, well, you can say it's by guessing now. Usually, yeah, if you don't know what to do, just by guessing. But actually, in your next semester, you will learn a systematic way how to get this solution. Actually, yeah, how do you change your font size? Interesting. Yeah, so you can type the big font to catch people's attention, to catch my attention if I'm like busy focusing on teaching. Okay, what time is it now? So let's work a simple example. 8.2.1. So this one is a standard and basic example. So let's see how to solve it. Why is it not showing? Yeah. So the example that we want to solve is hang on. Oh, I forgot to say something about the thing. So yeah, before I go to the example, let me comment a few things first. Okay. Yeah, so we do that later. My x of t, right? So my x of t is a cos omega t plus phi 0. Okay, so there's a few terminology that we should be using quite often here. Just now I already used the word, this is the amplitude. Okay, so the amplitude is telling us how big is the oscillation. So if A is large, so it oscillates over a big region, right? If A is small, the region is small. Okay, so this is the amplitude. And then omega, I already told you this is the angular frequency, right? And this part, this whole thing is called the phase. Okay, so we call this the phase, and then usually the phase is the function of t, is a linear function of t in this case. And of course, when t is 0, the phase is equals to phi naught. So this is the initial phase. Okay, so these are the names that I should tell you properly, because we will use these words quite often, right? So phase and initial phase. Is everyone clear with this so far? Right? If not, you refer to this picture over here, right? You can screenshot or whatever, copy this down. We will use these words quite often. So now let's look at example 8.2.1. Okay, so 8.2.1, how does it go? So let's see. So I have an oscillating mass of 1 kg, so m is 1, right? So 1 kg, and then it's attached to a spring at time 0 observed to be 1.5 blah blah blah. First, let me write down the spring constant first. The k is 2 newtons per meters, and according to the information given, right, it says that the position at 0 is 1.5 meters. So I will write x0 is 1.5 to the right, so I take positive, right? Positive. If I say right positive, then I have a positive 1.5, and then the velocity at time 0 is -2. It's going to the left, right? So it's -2 meters per second. Okay, so then from here, find all the information that is given there. So let me put this back. Okay. G equals has linear algebra. Oh yeah, we have a linear algebra for that covers GE. GE calls for linear algebra and also calculus. And is the content is almost similar, mostly similar. And the reason why it's offered, I suppose, is practical. But let's solve this first before we run out of time. Okay, so yeah, so given all this information, right, we can immediately get omega now. So omega is the square root of k over m. So k is 2, m is 1, so omega is just square root 2, right, radians per second. So that my expression of x of t, right, so is a is a constant, which we don't know, and then cosine, and then square root 2 times t plus my initial phase. Okay, so this is my position. So I will use this information later, but I also need the velocity. So let us get the velocity. So the velocity, right, the velocity is dx dt, and then it's just the differentiation of this. So I got negative square root 2 a sine, and then root 2t plus phi 0. Okay, so based on the information given, at time 0, this is 1.5 meters. So x0 is 1.5, meaning that a cos 0 plus phi 0. So I got this equation here. And then if I put this information for the velocity, v0 is -2, which means that it's negative square root 2a sine 0 plus phi naught is just this thing over here. Okay, so I got one equation and I got two equations. Okay, so to solve this, I just need to determine the a and phi 0. So using this method, I can determine a and phi 0. So 2 over 1. So if I divide these two equations, right, on the left hand side is -2 over 1.5, and then on this side is square root 2a sine phi over a cos phi. I can cancel the a, and I realize that my tangent phi 0, everyone becomes positive like this. So I got 2 over 1.5 square root 2. So from here you can compute the phi. So according to my calculator, my phi is 0.756 radians. Okay, so then I put this into equation 1. So x, equation 1 is 1.5 is equals to a cos 0.756, but must be careful, this is in radians. Okay, so if I cosine of this angle in radians, solving this a, I will get 2.061 meters. Okay, so I got my a and I got my phi 0 already. So my full solution is 2.061 meters cosine of square root 2 t, and then the initial angle was 0.756 radians. So this is my answer like this. Okay. Radians. Yeah, radians. 2 pi radians. Spin, yeah. I mean, you forgot radians already. So yeah, so I guess Wen Lan and others have explained already, right? Yeah, so 2 pi radians is equals to 360 degrees, right? So pi over 2 radian is 90 degrees and all that. What time is it now? 47. Okay. 3, 4, 5. So we have a bit of time, so I can talk about the energy of the harmonic oscillator. Okay, because we got the solution already, right? So yeah, so we have been solving a problem of mass m attached to a spring. Right, so and I have shown you that the force is F is equals to kx, and because this is a spring, we have learned about the potential energy. So the spring potential energy, right, if you remember, it is the negative antiderivative of the force with respect to dx, right? So the potential energy is half kx squared, and the equation that we are using, if you remember, F is negative du dx. Okay, so this is how this, from here I can get to here, or if I differentiate this and then negative sign, I get this F over here. Okay, so I get the equation for the potential energy, right? Then what is the, from here I can calculate all the information about the energy already. This is the x position, and just now I have shown you the solution, which is the cosine function. So the position of m is what? Well, is this formula again, right? So it's a cos omega t plus phi 0. Okay, so if you remember, omega was the square root of k over m. Right, so this is the position. So I can actually put in this position to calculate the potential energy at every single moment in time. Okay, then I can also calculate the velocity by differentiating this, because once I differentiate this, right, I get v, and then having the v, I can get the kinetic energy. So velocity of m is obtained by differentiating. So it's just negative omega a sine omega t plus phi 0. Okay, so the kinetic energy I can now easily calculate. Right, so the kinetic energy is half mv squared. So using this formula for v, I can put this into here. So this is equals to half mv squared. So right, so v squared, just square everybody. Like this. Okay, so this is my kinetic energy. And then how about my potential energy? right? So potential energy was half kx square. And then, yeah, so using this, too messy, right, if I do it. So using this x, I put it here. So I got half k, well, square, so a square cos square omega t plus phi 0, right? So now I want to get the total energy of the system. So total energy is everyone summed together. So I got u plus k. So I got half ka square cos square omega t plus phi. And then the k is everything here. So I got half m omega square a square sine square, this thing, the phase, right? And can I simplify or not? There's a half a square. And then there's a omega square. But remember, omega square is given by this formula. So if I put this in, I can recognize something to simplify. So I got cos square omega t plus phi 0. And then half m omega square is the square of this. So I got KOM omega t plus phi 0. So cancel the m. It's just half ka square. This is also half ka square. So actually half ka square can be factorized. Then I got cos square omega t plus phi, and then sine square omega t plus phi. What is this? This is equals to 1, right? So from here we have reconfirmed the conservation of energy. The total energy of a harmonic oscillation is constant, right? So the total energy of the system is constant. Is it clear so far? Yeah, is this one right? Yes. If this is r, then this is 1 radian. You forget me? We did use this before, right? In circular motion and the rotational motion. Angular velocity is radians per second. Yeah, so by the way, now is a good time to take a break. Yeah, 10-minute break. So I will stop the recording and we will continue with tutorial questions. Okay, so shall I talk about this again? Now we have time, so I can explain a bit more slowly this time. Because this is the question that is confusing to a lot of people, right? So let me try to do this again. Okay. And so remember, right, we have a plank on the roller. So if I pull the top part of the plank with some force F, it will roll over this thing. Okay. So the mass of the plank is big M. The roller each have mass small m and each have radius capital R. So these are cylinders. So cylinder means the moment of inertia is half mr square. And in this question, everybody is no slipping. No slipping means one thing is static friction everywhere. Okay, and also because this is no slipping, right? This is the part that a lot were asking about. Why what is the acceleration of the plank? So let's say, right, this is the velocity of the center of mass. Okay, and if this is no slipping, pure rolling, then the v tangential is equals to the v center of mass. Okay, so that is the tangential point. What is the total velocity of the point on top, right? So the total velocity of the point on top is let's say v on top. Well, the total velocity on top is just the v tangential plus the v center of mass, right? And therefore, what is the magnitude of the speed on top? So if both are pointing the same direction, then the total velocity is just 2v center of mass. Do you agree? Right? And also I have shown you the animation last time, right? The v at the bottom is equal to 0 because they are cancelling each other, right? So do you remember this? Okay, so that is for the rolling cylinder. So how do you get the velocity of the plank? Because the plank is sitting on top of this part, right, and then it's just dragging over the thing. Therefore, we conclude that the velocity of plank is equals to the velocity at the top, right? So v plank is equals to v top, and v on top is just twice the velocity of the center of mass. So that is for the velocity. How do you get the acceleration? The acceleration of the plank is obtained by differentiating velocity. So it's differentiating both sides of the equation, and this is the acceleration of the cylinder. So a plank is equals to 2a. Is this clearer now? Okay, so that is the acceleration of the plank. This is the acceleration of the cylinder. The center of mass of the cylinder. So if you get the acceleration of cylinder times 2, that's the answer for the plank already. Okay, so now let's try to solve this system, right? So let us begin by solving by drawing the cylinder free body diagram and see what are the forces acting on the cylinder. Am I recording? Yes. V plank is V tangential of the wheel. Yeah. No. Total velocity of the wheel. V tangential plus VCM. Yeah. Then you differentiate both sides. Okay. Recording? Yes. Yes. I think so. Yeah. Yeah. Okay. Now let's draw the free body diagram. Right. So as I was saying, right, this is the center of the cylinder, and then there's a radius r. So there's two forces acting on it, right? And then everybody don't like that I draw the two forces pointing forward, right? So okay, fine. Then I draw this force pointing forward here, and then I draw this force pointing backward here. Okay, so if you don't like, maybe you will feel happier if we do it this way. And then the radius is r. So from here, let us try to solve the system. Okay, so let us try to write the horizontal forces. So horizontal forces, we take the right as positive. Okay, so now if I draw it this way, right, then I got F1 minus F2, right, is equals to the total mass times the acceleration of the system. So the net force is F1 minus F2. By Newton's second law, the net force is ma. So I got this first equation over here, right? And then next thing, we analyze the torque on the cylinder. So we will take clockwise as positive. Okay, so if you take clockwise as positive, what is the torque? So this is the force that you can imagine, it tends to push it in the clockwise direction, right? So this force is a clockwise torque. This force is also a clockwise torque. So this torque is r times F1 because it's perpendicular. This is also plus r times F1. It is also perpendicular, and the distance is r. So the torque is equal to I alpha. So it's equals to I alpha, right? So let me write one more line. F1 plus r F2. And then the moment of inertia of the cylinder is half m little mr square. And then alpha is a over r. So because this is pure rolling, alpha is a over r. Right, so we put this here. So this becomes a over r. Then now we do cancellations. So I got F1 plus F2 is equals to half ma. So this is equation 2. Right? So this is the cylinder. How about the plank? Right? So the plank is just something, and then you're pulling it with a force of F. And it is touching F1. So F1 is here. There's two cylinders, so there's two F1s. And then if this is forward, we must obey Newton's third law. By Newton's third law, if this is front, then the other one is backwards. Okay, so the horizontal force on the plank, right, so I got one equation, I got another equation, and the force on the plank is F minus 2F1, and then this is the big M, and then just now I have convinced you that the acceleration of the plank is 2A. Right? So F minus 2F1 is equals to 2MA. So this is my third equation. Yeah, left. So here is not really right hand rule because you can define your direction as long as it's the same. So right hand rule is telling you the vector like this, so it's pointing this out. So that means if I actually it's not really nothing to do with right hand rule. Right hand rule tell you the vector. So if rotating clockwise, right, that means my axis of rotation, if I follow my right hand rule, my vector is pointing in. Okay. But then, right, if I use right hand rule, if I look at the picture from the other side of the cylinder, then it becomes negative again. So it's just, again, it's still a convention. Yeah, so if I say clockwise positive means if I get a positive omega, it just means it's rotating anti-clockwise. You can go back and try and see. If you define anti-clockwise positive, then this alpha should be a negative sign because this thing is rotating forwards. Oh, the rotation matrix. Yes. Yeah, so anti-clockwise is positive. Yeah, but we are not really talking about the axis of rotation here. We are just talking about the magnitude, alpha, the alpha. Okay. Yeah, I know what you mean. It's slightly different. So the rotation matrix is cos theta, sine theta, cos theta. So if theta is positive, then you're rotating this way. If theta is negative, you're rotating the other way. So that is a different thing. Okay. But anyway, right, I got three equations. So let's solve this. Right. So three equations. Well, I can settle these two equations first. Let me take equation 1 plus 2. So if I take 1 plus 2, right, so I get 2F1. So this plus this cancel. And then the right hand side plus right hand side, I got 3 over 2 MA. Can you see? Right, so this plus this gives me 3 over 2 MA. And just nice, I can substitute this straight into equation 3. So if I substitute into 3, I get 3 over 2 MA. This is 2, big M times A. So if I times 2 to everybody, 2F minus 3 MA is equals to 4 big MA. So I got my A is equals to 2F over 3M plus 4M. So if you put in the numbers, right, the force is 6 newtons. The small mass is 2. The big mass is 6 kg. So if you calculate everything, you will get 0.400 meters per second squared. Right? So this is the same answer that we got last time. Okay, but how to get the F? So let us take this equation and solve for F. Let's see whether we get correct or not. So my equation here is 2F1 is equals to 3 over 2 MA. So I put this A into here. So I got 2F1 is equals to 3 over 2. The little m is 2 kg. The A that we got is 0.4. We got F1 is positive number 0.6. Also the same answer that we got last time. Right? And then now we substitute our results. 0.4 into equation 1. Right? So my equation 1 was this thing over here. Right? So I got 0.6 minus F1 is equals to M and 0.4. So if you this F2. So if you calculate F2, right, you bring this over, you will get 0.6 minus 0.8. So the answer is negative 0.2 Newton. You got a negative sign, right? You got a negative sign means it is a negative of this direction. So the correct answer is is here. So it's 0.2. The magnitude is 0.2 Newton. You get what I mean? So you don't really need to care what direction you are putting it in. Okay, so if you're still not happy, right, then fine. Let's solve this again. So let's repeat the question again, but this time I draw another direction. So now let's do it. How about both pointing backwards? Okay, so both pointing backwards. Then what is the cylinder equation? So what is the net force on the cylinder? Now is both are negative, right? So both are negative. I got minus F1 minus F2 is equals to MA. This is my equation 1. This is horizontal forces. And then the torque on the cylinder. The torque on the cylinder, now it is, again, we are still using clockwise as positive. So this is an anti-clockwise torque. This is a clockwise torque. So F1 is negative plus F2 and is equals to I alpha. So minus F1 plus F2 is half mr squared. Alpha is still A over R. Oh yeah, I forgot to times R. So if I cancel all the R, I got negative F1 plus F2 is equals to half MA. That is the second equation. Right? And then let's look at the force at the plank. So the plank force is still pulling forward to the right at F. And then now my F1 is to the left for the cylinder. So by Newton's second law, it should be opposite now. F1. So by Newton's second law, now I got F plus 2F1 is equals to MA. 2MA. Right? So this is equation 3. So if I now solve, well, let's take 1 plus 2 again. Because 1 plus 2, 1 plus 2, I will cancel the F2, so I got negative 2F1 is equals to 3 over 2 MA, so that my 2F1 is negative 3 over 2 MA, right? And then I will substitute this into 3. Okay, let's see what you have. Plank is not equal to cm, yeah, right? The acceleration of the plank is twice of the cm. Yeah, in a sense, I'm kind of wasting time now. Equation 1 not equal to equation 3, yeah. Equation 1, yeah, they're not, this is, well, I should say this, right? So this is M A plank. And then A plank is 2A, so I substitute this into here so that my F plus 2F is equals to 2MA. Okay, so then this is your equation 3. Right? So I substitute this into equation 3, so I got F minus 3 over 2MA is equals to 2MA. So I get back the same equation, right? So 2F minus 3MA is equals to 4 big M times A. So your A is 2F. This one becomes plus, so I got 3M plus 4M. So this is still the same answer. What was it? 0.4 meters per second. Right? And then I put this into my equation 1. So what was my equation 1? No, this equation. So this equation. 2F1 is 3 over 2MA. Right, so my 2F1 is equals to 3 over 2, the mass is 2, the A is 0.4. Then you get F1 to be negative now. So negative 0.6 newtons. right? And then we put this into equation 1. So our equation 1 is minus F1 minus F2 is equal to MA. So I take this F1, put it into here. Take this A, put it into here. Negative 0.6 minus F2 is 2.4. So my F2 is 0.6 minus 0.8. So F2 is also negative 2 newtons. Okay, so I got two negative on F1 is negative, F2 is negative. So F1 is negative, that means it should be the negative of this. So F1 I got the negative number, I should draw it, the correct arrow should be like this. F2 also I got a negative number, so the correct arrow should be like this. Okay, so hopefully it makes a bit more sense now. The direction, this is static friction, so yeah, the way you guess it, it doesn't matter because the sign will tell you that your direction is wrong, right? I got a minus number for my magnitude, so that means my arrow is wrong, so it should be pointing the other way. Right? Any question? Okay, understand? Okay, Jia Cheng, understand? At least the equation 1 and 3 part, right? So linear algebra, you got week 12 assignment, right? And yeah, so for us it's week 15, the last day of the semester. Why bad news? You haven't started. Okay, it's fine, plenty of time. At least you should start thinking about it lah. Then when you start you have a better picture. Okay. Yeah. So plenty of interesting questions hopefully for you guys to explore. So let's do some gravity tutorials. Summer assignment. Oh. 20-30 page. So mine should be very easy, right? Mine is like I say 1 to 2 page, but I uploaded the sample, so yeah, you get the style of writing in comparison. Yes. Oh. Yeah. So so let's do was it tutorial 7? Yeah, tutorial 7. Am I recording? Test. Still running. Oh. Calculus also got assignment, is it? Actually, yeah, the sample is one of the topics, so for that topic already got the answer, but see what else you can add on to it, right? Obviously you cannot just copy the same sample and give it back to me, right? Makes no sense. Oh, if you open a bottle in daily life, is it torque? Yes. Yes, it is. So the yeah, because it's a rotation, right? And it's because, right, the bottle is stuck, the cap is stuck there because of the friction. And you need to rotate the bottle, so you need to give it more friction, and your friction with the cap must overcome the friction of the cap with the bottle to open it up so it can rotate. Then once you rotate, yeah, then after that is the groove that follow the thing, then it's just, that's how it works. Need how many page again? Minimum 2. Yeah, so but of course in my case, right, the project won't be based on how many pages. Otherwise you just like, people will just write nonsense and make it many pages. What I want to see is your content, right? What are the results that you study, what you read up, whether it's long or short. And then yeah, so this type of situation, that means content is very little, right? So, and it's very is it substantial or not? So must be something, yeah, must be something relevant. So the sample I gave, right, is 6 pages, because like if you type it out also, it will fill up the thing. Okay, so now let us do some assignment from the gravity part. Okay, so let's do question 2. First is no assignment, be heated. What do you mean? So for the thing related to gravity, right, I guess, you know, most of it are pretty straightforward. So let's do question 2. Let's do question 2, and then let's see how we go from here. Okay, so question 2 goes like this. Let me okay, so according to question 2, right, we have a 8 kg point mass and a 15 kg point mass 50 cm apart. So a particle of another mass m is released from a point between the two masses 20 from this thing. So find the magnitude and direction of the acceleration. So we should be able to work this out based on the info given. So according to the question, right, I have 8 kg. So let's say m1 is 8 kg, and then 15 centimeter away is 15 kg. So it's m2 is 15 kg, and then there's a little m here, right, that is 20 cm away. So R1 is 20 cm away from this mass, and the total distance from here to here is given also, is 50 cm, right? So obviously this should be what? This is 30. So this is R2. Okay. So then we can easily calculate the force. Once we get the force, we get the acceleration. So let's calculate the force on the little m. So remember, what is the gravitational force? The gravitational force, well, I have two objects over here. So there's a force coming from m1, the gravitational attraction, and another force coming from m2. So this attraction, right? And one is pulling that way, one is pulling the other way. So it is F1 plus F2. So let me define my axis. My axis, let me call this my positive x direction. Then once so this one hopefully to make you practice writing vector. The F1 force is m1 over here. So everyone knows what is the magnitude, right? So the magnitude is g, the m1, and then the little m, and then the distance square. So that is the magnitude. How to get the direction? Well, if this is along my x-axis, it is in the I direction to the left. Do you agree? Right? I direction to the left. So I got this equation here. Okay, so this is F1. How about F2? So F2 is to the right. So it should be m2 times m r2 square in the I direction as well. Okay, it's positive because it's pulling this to the right. Okay, so hopefully everyone is familiar with vector, right? We keep on using vector everywhere, so good time to practice. Any question? Nice. Yes, it is similar to Coulomb. Yeah. So yeah, so because this one is very similar to Coulomb's law, right? So that's why. So if you are familiar with it, then should be good news. So let me simplify the equation. We notice that, well, I can simplify by taking out the common factor. So I got minus m1 over r1 square plus m2 over r2 square. And all this is in the r direction. But actually we got the numbers. So I got gm, and then m1 is 8 kg, right? So 8 kg divided by r2 square. So r2 square is 20 cm. 20 cm is 0.2 meters, right? So it's 0.2 square. And then this is 15 kg. Remember to convert SI unit, right? Important. Newton's law is in SI unit. So we got 0.3 meters. Okay. So after you work out this number, you get minus, if I'm correct, is minus 3.33 and then times g times m, and then I. Okay, and then also if you're we should put in g is 6.67 times, I can never remember, right? So put this into here, and my equation, my vector equation for force is this times this, so it gives me negative 2.22 times 10 to the minus 9, and then times m. Notice that the m of this small mass is not given, and actually we don't need, because we need the acceleration, right? So we use the second law. So second law is F is equals to ma, and at the same time is equals to this. Okay, so times mi. So the m will cancel, so that this a will give me in meters per second. So it's minus 2.2 times 10 to the minus 9 meters per second square, and all this is along the I direction. So we notice that our answer got a negative I direction. This is the magnitude, it is towards the left. Okay, so as you can see here, right, this mass, well, this object is heavier than this object, but it is nearer. Okay, so it's nearer. So what is the net force, right? So is it, if this force stronger or this force stronger? It turns out that is this number that is stronger. Okay, so this is why we got the negative acceleration. It is going towards the left. Okay, so any question about this? Okay, so if not, then let's do the next question. This one is also, I think in Coulomb also they will give you this type of question, right? Number 3. Okay, so for number 3, right, they give you this problem. So let's pull up this question. So a particle of mass 3m is located 1 meter from, oh, hang on, a particle of mass m. Okay, and then where should I put a third mass, big M, so that my net gravity force is 0? And then the rest, you just, once we answer the first part, the rest should be quite straightforward. So let's solve this. Okay, so I have a particle of mass 3m, and it is located 1 meter away. So from here to here is 1 meter. Okay, and then I want to put a third mass, and I don't know where to put it. So let's call this position X, away from full screen. Let's call this position X, away from the 3m mass. So if this is X, then what is this? 1 minus X, correct? Okay, so again, now let's look at the net force again. So yeah, so let's write the net force. Okay, so the total force is F1 plus F2. So the first force is attracting to the left, then the other force is acting to the right. So we have well, the first is negative g big M and then 3 small m over x square, right? And then the other force, well, this is in the I direction, right? So if I take this as my x, then the other force is to the right, so it's positive g big M, and then this is just the m, but the distance is where you must be careful. The distance is 1 minus x square, and also in the I direction. Okay, so I can simplify this equation because notice that everybody got a factor of gmm, just that this part is 3 over x square, so this is 3 over x square plus gmm, take out, I got 1 minus x, the whole thing square in the I direction. Okay, so I want zero net force, so zero net force. So zero net force means I want this thing to be 0, which is to say that 3 over x square is equals, well, plus this thing, I want this to be 0, right? So let me try to simplify this a bit. I got 3 over x square is equals to 1 this thing square, which is to say that 1 minus x square is equals to x, hang on, yeah, this one must be careful. Square is outside, right? Because I need to open the bracket later. So square of this is 1 minus 2x plus x square, and I got x square over here. So this is 3 minus 6x plus 3x square is equals to x square. So if I bring this over, this becomes 2x squared. This is a degree 2 polynomial, and then plus 3 equals to 0. Okay, so I just need to find what is the x that can give me this solution. So let's solve for x. Well, I can use the quadratic formula. Remember the quadratic formula? X is equals to minus b plus and minus this thing, right? Okay, so I'm going to do this for this part. So x is equals to negative b, so it's 6 plus and minus b squared, so 36 minus 4ac, and then square root, and then 2 times a, so a is 2. Okay, so this one, usually most of the time we can simplify this a lot. This is 36, 12 times 2 minus 24 over 4. So this is 6 plus and minus the square root of 12 over 2. And this one can simplify a bit. 12 is 4 times 3. Square root 4, I can take it out. So square root 4 becomes 2, and then times square root 3. And then divided by 2. Wait. Why change back to 2? This is 4, right? Yeah, this is 4. Correct, right? This is 4. Yeah. So that I can, so that it becomes this. Right, so it's 2, 3 plus and minus root 3 over 4. So this becomes 2. So my answer is half 3 plus and minus square root 3. Okay. Any question? So still okay, right? Now, here's the tricky part. Okay. Here's the tricky part. There's 2 solutions, but only one of them is physical. So only the solution x is less than 1 is physical. Okay, so that means we reject because 3 plus root 3 is, what was the number? I don't remember. Yeah, it's like 2.366. It's greater than 1. Okay, so we reject this solution. So the answer that we're looking for is half 3 minus root 3. So this is 3 minus root 3 divided by 2 is 0.6339. Okay, do you know why I reject the larger solution? Can anybody guess? It's a tricky, yeah, it's not very obvious, or it's either obvious or not obvious. I also don't know. It wasn't obvious to me at the beginning when I was learning this for the first time. No guesses? Okay, so the reason is this. Okay, the solution that we got right is here. Okay, so I have 3m, and then I have m over here. So this is, if this is distance of 3 minus square root 3 over 2. So this is my solution 1, right? And then my other solution is over here, right? So I should do it this way. So this is my 3m, this is my m, so this position is x equals to 1, right? So if I take x as my origin, so this part is 3 minus root 3 over 2, and then this part is 3 plus root 3 over 2. Okay, so this solution is outside of this thing, and then there's two ways to look at it, right? This is the solution that gives you the zero net force, because you have the force here and force here, they cancel each other out. But then if I have my object mass, if I put it here, right, the force coming from m is F1 over here, and another force coming from m F2 over here. So how can this be in equilibrium? Cannot, right? So that means this one is no such thing, so it cannot have this solution. Okay, then you think back, how can this contradict our equation just now? Did something went wrong with our equation? Something did went wrong. When we derive this, right, we put a positive sign here and a negative sign here. Okay, but it is no longer consistent with this case. If I put it here, right, then the two forces must be negative. So that's why you reject the solution with the that is outside the two masses. Okay, so hopefully it makes sense to you guys. Then this, my answer is 3 minus root 3 over 2. So the answer to A is 3 minus root 3 over 2. Okay, now we answer B and C. Because 1 minus x is negative, yes. Yeah, that is the another reason. And then the larger one is not between the two objects. That's why. Yeah, if we don't, right, then the two forces cannot cancel each other. The larger one won't fit in the equation direction. Yes, exactly. Yes, yes. That's what I was saying. Because the larger root will not, it doesn't come to this. It will be contradicting this solution over here. So these are like the little things that you must take care of when you solve the solution, you know. Right? Why we have the inconsistent solution? Yeah, so yeah, because this, you know why? Because, right, first of all, there's a square in our equation. So so the square will, it will sort of like, you lost information from this thing already. Okay, that is one reason. And then the other reason is, well, we started off the entire process by putting one negative and putting one plus, right? So we are assuming that the two forces are in different direction. Okay, But if I get the solution here, right, this is where the two forces are negative actually. So you cannot get the, it is not consistent with what we start writing in the first place. Okay, so yeah, so that's why. Make sense? Does it make sense? Understand? Okay. Then okay, so then the last thing to talk about is, I guess good news for you guys. This one no math. We can answer the question by thinking of this: is the equilibrium at this point stable or unstable along the line connecting M or 2M? So what this question is trying to say is that voilà, 3M and then single M, and then if I put this as 3 over root 3 over 2. Okay, so if I move this along the line of, is this stable in this direction or not? So we are talking about the forces in the horizontal component. Okay, so for part B, we are talking about horizontal forces in the horizontal components. Okay, so 3M and M. So we're talking about forces, horizontal forces. Okay, so if I move this slightly to the right, okay, so how do we say, let's say, okay, so if I, this is small m, right, this is small m, this is big M. So if I move this slightly to the right, what is going to happen? So original position, 0 force. Okay, original position, 0 force. But let's see what happens if I move this slightly to the right. So if M is displaced slightly to the right, then this force, right, this force was F2, is stronger than this force. I mean, I'm drawing it in pictures so that it's easier to understand, but can you imagine, right? If M is moving slightly to here, it is nearer. It is nearer, so the Newton gravitational force will make it a stronger force. And then I move this further away, then it is weaker. Okay, so it is weaker, then also it will be weaker force, so it will get pulled towards this, right? So then the net force in the new position is towards the M. Okay, so the M keeps getting pulled towards M all the time, right? So all the time, and this is why this is an unstable equilibrium. Yeah, like a mountain peak on the rolling stone. Yeah, so because the potential on the left and right is higher, is lower, so it will keep on going like this. Okay, so this is the answer is the equilibrium is unstable. Okay, so that is for part B. How about part C? So part C, right? Part C is telling this. Is the equilibrium along the point passing through M and perpendicular to the line connecting this thing. So the picture is now in the y direction. So this was 3M, right? And then this was single M, and then my position that we calculated was M. But now I'm talking about the displacement along this direction. So this is my y displacement. Okay, so this is vertical displacement. Okay, so vertical component. Now this equilibrium is actually stable in the vertical direction. Why? Because, right, if M is displaced upwards, okay, if m is displaced upwards, then there's a net vertical force downwards. Can you imagine? Right, so if you can't, I will draw. So I got 3m and then m over here, and then I displace m if I move it up, right? So I move this up over here. If I move this up, then what's my forces? So my forces now is F1 to here and F2 to here. So if I resolve, right, then the horizontal forces is still the x is still the same, so they cancel each other. But then I can resolve this force. There's a net force pointing down. Okay, so it will pull it back down, right? And it was the same if I move it down. If I move it down, right, then my net force is, well, there's two components here. So if I resolve it, is pulling it down. Okay. So there's always a net vertical force pulling it back towards equilibrium position. Okay, so therefore the equilibrium is stable in the y direction. Okay, is it clear? So the horizontal direction is unstable because they are two trying to pull each other, right? So they cancel a force. But if you move one nearer, then this part will become a stronger force. So you continue to get pulled all the way there, right? Same thing for the left. But for the vertical direction, right, if you shift it up a little bit, then there's a net force to bring it back down. So this one is like a restoring force. Coming back to what we talked about in chapter 8 in the beginning of today's class. So it's something like restoring force, because every time you move it out of the equilibrium, it will try to push it back. So that's the restoring force. Okay, any question? Yeah, just out of time. Show B again. Yeah, B is here. So if I draw in pictures, right, for B, okay, so if this is my equilibrium position, then the net force is 0. But if I shift it, let's say I move it a bit here, then this force is stronger than this force. Okay, so you get it now? Oh, my handwriting here is ugly. This is little m. Yeah, horizontal component. This is the vertical component. Your eyesight. Oh, is it? Yeah. Unstable and stable. So you need specs, is it? Okay, good. Anyone else? Is everyone follow so far? Follow, Okay, good. That's great. Okay, so yeah, gravity chapter, I guess, is easier compared to the other chapter, is it? That's why I can follow. Because it's just one equation, right? So it's always the same all the time. And I guess in that sense, gravity is easier to understand. Easy integral. Yeah, right? Yeah, I feel the same. Definitely easier than chapter 6. Yeah. Okay, so yeah, chapter 6 is quite hard. And probably the hardest is the hardest. COR integrate become ln R. Or in the tutorial. Oh, in one of the questions, is it? If you integrate, I think what you mean is this part, because yeah, and also this part. So these two parts are the hardest. Okay. Okay, so the rod is really hard. Yeah, but it's the hardest. But again, right, it's hard, but it's only one question, and usually, it's always like the rod, and it's every time you see the rod, the method is going to be the same. So once you get that one method correct, then it's fine. So besides that, if there's no other question, then that's all for today. So yeah, so we will continue on Monday. We will continue talking about oscillations, and then Wednesday there's a quiz, and our class starts at 4 p.m. And then meanwhile, there's nothing much, just a quiz, and then yeah. So now is the time. Even if you haven't started the assignment, should start thinking about the assignment. Where is the application in physics? Linear algebra. Well, circuit is one thing, yes. Vector space. Well, all the forces that we are talking about is in vector space. String theory, definitely a lot of linear algebra, and in fact, algebra. Kirchhoff law. Linear algebra. Well, maybe I can tell you this. I guess I will stop recordings.